Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about complex roots of unity. We all know how to solve basic root questions. If I ask you something squared is 1, you know that the answer is 1 or -1. Both of those squared is equal to 1. But once we start getting into higher powers, if I ask you what to the 4th power is 1, we'll look at that later. You can probably answer that question. But how can you be sure you have all of the solutions? And these things get pretty complicated as you have higher and higher powers. That's what we're going to be looking at today when we're talking about these complex roots of unity. Little review to start. Remember that any complex number we can write in rectangular form and also convert that into polar form. So that is what we can do for these different types of numbers. When we have it in polar form, we then have the modulus. So that is our radius in a sense, the distance from 0, and theta is the argument. So we oftentimes think about both of these forms, even rectangular, the normal form, or polar form. We think of these often as then something you can graph and view in the xy plane, which then becomes the real and imaginary plane. So if we have a number here, for example, let's look at the complex number z, which is, let's just do a simple one, which we'll revisit later. Let's say we just have 1 plus I. So this is pretty easy to graph when we have 1 plus I here. And so this is our point then, 1, 1. That would be our coordinate there. Now for converting this into polar, we have 2 questions to ask. First of all, what is the distance from the origin? What is the distance from 0? This is the argument. The argument is, of course, here square root of 2. 1 squared plus 1 squared square root. This is our modulus in this case. What about the argument? I was getting a little bit ahead of myself there. This one's also pretty straightforward because we have 1 and 1. This is some trigonometry type stuff, but we have, in this simple case, a 45-degree angle. That is going to be our argument in this scenario. We have our modulus, the radius, the distance from 0, argument, the angle. This is the angle from the x-axis for our complex number there. So with this in mind, then let's just write out what the z would be. This is, of course, then square root of 2 times cosine of 45 degrees plus I sine of 45 degrees. So we have I times sine of 45 degrees. Now, one of the powerful things about this, on first glance, it doesn't seem like this is very useful. What's the point? We could graph it even easily in a plus bi rectangular form. What's the advantage of polar form? The real advantage comes in this next observation. And this is also something we reviewed in the polar form video, but the power here comes when you're multiplying. If we have 2 complex numbers, a first complex number here written in polar form, so r cosine theta plus I sine theta, and then we have one in polar form as well, s times cosine of phi plus I sine of phi. So we have 2 different angles there. Remember, when we multiply the moduli and add the arguments. So when we multiply this out, we end up with r times s, and then our argument, our angle, is theta plus phi. So that is where we come up with a pretty nice way of multiplying complex numbers when we have them written in polar form. And this is the true advantage, right? We are now adding angles, so we're doing some rotating, we're doing some scaling, everything can be interpreted in that geometric way. The specific thing we're going to talk about in this video, the rest of this video, is this same formula but applied to the special case of raising a number, a single complex number, to a power. This is sometimes called de Moivre's formula or theorem. It's really, though, just the special case of what happens when we multiply the same number by itself. Then, of course, when we have that original modulus, when we have the original r, it gets raised to a power. So we have this raised to r to the nth power there. So r becomes r to the nth power. And for our arguments, for our angles, of course, repeated addition is just multiplication. So the argument in the nth power of this number is n times the original angle. And so this we can start having nice observations for. We have nice relationships between a complex number and its power, and that is what we're going to be exploring when we get to these complex roots and the roots of unity in particular. But let's do one example again where we're taking this in the forward direction. So let's look at our number z again that we started to look at and examine before. So we had z equals 1 plus I, and remember this had a modulus of 2, square root of 2, and then we have cosine of 45 degrees plus I sine of 45 degrees. Now, we're not going to write out all of these examples there. I will write out one of them because then we can start seeing the pattern. But a lot of this is much better done if we are just thinking about our graph again. So let's actually view all of this again in our complex plane. So let me give enough room for at least one example there. And I guess I can move my axis down a bit, which we'll see in a second. So that is what we have then as far as our xy plane. And we can start with our point 1, 1 as well. So that was our z at the beginning, was this point right here. And I'm going to write it in just polar form here to save a little bit of space. So this is the point in polar form, square root of 2, 45 degrees in this scenario. Now, these numbers can be a little bit messy in rectangular form. So we're not going to focus so much on exactly what they are in rectangular form. You could calculate it when it's nice angles. You could do approximations if you have messier angles for using a calculator. But using de Moivre's theorem, if we look at z squared, again, let's not focus on the rectangular form. Let's focus on the polar form. Well, we square the modulus. Square root 2 squared is just 2. So square root 2 squared is 2. And then our argument is just double 45. 2 times 45. So this is cosine of 90 degrees plus I sine of 90 degrees. You could, of course, convert this pretty quickly back into rectangular form. Cosine of 90 is 0. Sine of 90 is 1. So this is actually just the number 2i, which you could double check by squaring 1 plus I there as well. So let me contradict myself a little bit, and I can squeeze in. This is actually 2i in that case. But the real point I want to make here is that you can then look at this in terms of our xy plane as a pretty easy point to look at. You take our 45-degree angle, square root of 2. It gets rotated another 45 degrees and stretched out by a factor of square root of 2. So our second point here, our z squared, is going to be in polar form 290 degrees. And hopefully everybody sees that this pattern is going to continue from here. I'm not going to label them above, but if we look at our next point, so if we look at z cubed, well, we're stretching out by another factor of square root of 2. So if we stretch these things out a little bit more, we are also rotating by another 45 degrees in this case. So our next point out here is going to be, well, we have a radius of 2 square root of 2. That is our radius, r, the modulus, however you want to say it. And our angle is 3 times 45. So we have 135 degrees in that case there. Then you probably see where this is going. Oh, sorry, let me label this as our z cubed then in this case. So here we have z cubed. And then we also are going to have z to the 4th, of course, at a 180 degree angle. So we've come all the way around to the bottom here, and we have the point z to the 4th, which is going to be 4. So let's be a little careful that typically the modulus is positive, and then we have 180 degrees in this scenario. So that is our points that we're looking at here. So just to clarify our graph, this point here is our z squared, and then our original point was z at the bottom. So when you are raising to a power, you might be doing some scaling based on the modulus, but then otherwise things are rotating around in that case. And I just want to say, if you're not changing the modulus, which is what we're going to look at in later examples today, if you're not changing that modulus, actually you're just rotating around a circle. And this circle picture is going to be very important when we want to start thinking about roots of unity in the next couple of examples. Okay, let's look at our first roots of unity. These are fairly simple again. We have x to the 4th equals 1 in this scenario. Now I want to point out, I don't want to make it seem like you have to use this method always. When they're simple enough, you can use algebraic techniques. So if you're solving this, you might say x to the 4th minus 1 is 0. When you're looking at the factoring, we can factor this as x squared minus 1, x squared plus 1. And from there, whether you continue factoring it or not, it's not too hard to see that this gives us solutions of x equals plus or minus 1. And then we have x equals plus or minus I. So we have our 4 roots that way in terms of plus or minus 1, our normal square roots of 1, but then we also have plus or minus I in this scenario. Now I want to write these in polar and rectangular form. Well, really I want to write them in polar form here and look for some patterns. Of course, all of these have a modulus of 1 because we have just plus or minus 1 or I in this case. I'm going to put them in a specific order, which we'll hopefully see why in a second. The first one is I. So I is 0, 1 if we're looking at rectangular points. So this one is going to be an angle of 90 degrees. So we have cosine of 90 degrees plus I sine of 90 degrees. Okay, so what about negative 1 then? Well, negative 1, this is going to be an angle of 180 degrees. So we have cosine of 180 degrees in this case, and sine of 180 degrees. And hopefully by now you can see the pattern. So try to guess which one I'm going to do next. It of course is going to be negative I as the next one. And this one is going to be cosine of 270 degrees plus I sine of 270 degrees. Now, I could have started or ended with the last one, which of course is just the regular number 1 in this case. And just to follow the pattern, and this will be a good comment to make anyway, we could think of that as an angle of 0 degrees. But of course, 0 degrees is also, or could also be written as 360 degrees in this case. So just to find our pattern here, let me write it as 360 degrees for now. But of course, that could also be 0 degrees as well. So maybe let me write both even. So this one you could have cosine of 0 degrees plus I sine of 0 degrees there. Now, let's highlight this first and last one again. So I want to give a little preview, and this is how we're going to solve some of these when the numbers get a little bit messier here. Let's look at, for example, the first one here. Let's look at cosine of 90 degrees plus I sine of 90 degrees there. And let's look back at our original equation. Remember, we're trying to solve x to the 4th equals 1. But let me write it now as a complex number. Let me write it, of course the modulus is 1, but let me write 1 as our last expression. And I actually want to write it with the 360 degrees plus I sine of 360. Now, why do I want to write it like this? Well, we said by de Moivre's theorem, when we raise something to a power, when we have x to the 4th power, we multiply the angle. We multiply the argument there. What's the reverse of multiplying? The reverse of multiplying is dividing. So instead of multiplying the argument, if we want to take the 4th root of both sides, we can divide the argument. And so we can get cosine of 360 degrees divided by 4 plus I sine of 360 degrees divided by 4. And that actually would give us our first root there. This x is solution there is I. That is cosine of 90 degrees plus I sine of 90 degrees there. So we actually have a way of taking this square root there. And this method works in general. We can do this type of idea in general. The one thing we have to be worried about is that we actually don't have just one way to write the number 1. Already on this screen, I said 1 could be cosine of 0 plus I sine of 0. But it could also be cosine of 360 plus I sine of 360, etc. And so we just want to do that and be careful with that in the general case. And let's do that quick with this example here for x to the 9th equals 1. Now, notice this should have 9 solutions. It's a 9th degree equation, so we're looking for 9 solutions here. And so the issue here now is that we need to do this if we want to have our strategy of writing this as, well, x to the 9th is cosine of 360 degrees plus I sine of 360 degrees. We can do our same trick as before, right? And we can say, okay, we have x to the 9th is that, so we take the 9th root of both sides. We have cosine of 360 divided by 9, so that is going to be 40. So we have 40 degrees here, plus I sine of 40 degrees. Now the issue is that we only gave one solution then there, right? This gave us one solution. We're supposed to have 9 in this case. There's different ways to do this. You could say, well, what happens if instead cosine is, the angle is 0? or 720. We can actually do that really quickly with some variables. Actually, this works for any multiple of 360. This actually works then, we can write the equation 360 degrees times k plus sine of 360 degrees times k. Just to keep track there, notice that, well, if we wanted to start with 0, we could start with 0, or 1 would work, or 2, all the way up to 8 in this scenario. And now everything we did works, except we just need to add a k to this equation as well. And so in fact here, any of these multiples of 40 will be okay. So we have k equals 0, 1, 2, all the way up to 8 in this scenario. So these are the 9 solutions. Remember I said this can get a little bit messy. This doesn't have nice rectangular forms because cosine of 40 degrees, sine of 40 degrees, that is not really a nice number there. Quick comment about the k values. Do you really need to worry too much about what happens for those k values? Not really. Why do I say not really? Well, what happens when k is 9? When k is equal to 9, we have 40 times 9. That's 360. So actually, even if you use different values of k, that pattern's going to be repeating. So if you're a little confused which values of k work, you can just start listing out the multiples of 40, right? So 0, 40, 80, and then you do that until you get a pattern, remembering that everything repeats 360 degrees in this unit circle there. And it is good to think about those angles as spaced around the circle. Our 9 roots are going to all be points spaced around the circle because they're all modulus 1 and arguments are multiples of 40 there. To wrap this up, just note that this general thing works always. These are what are called the nth roots of unity. So the n solutions, some of them are they're complex. You could have real solutions. Often 1 or -1 is a solution if n is even. And these are equally spaced around our unit circle, and they're all these multiples of 360 divided by n. So in the last example, we looked at n equals 9. We also looked at n equals 4. So when n was 4, we had multiples of 90 degrees around our unit circle. When n was 9, we had multiples of 40 degrees equally spaced. But this works in general, and this is a great way to start getting more comfortable with complex numbers and is one of the most powerful things when you're talking about polar form. It's the most powerful thing you can do when thinking about complex numbers in polar form. Thank you all for watching. Check back each Thursday for a new math tidbit, and if you're looking for some more practice, check out ziml.areteem.org. We have a lot of great things there as well. If you like this video, please subscribe to our channel to stay updated on everything, and I will see you guys all next time. Goodbye.